The first speaker of this second morning session is Jonathan Ferreira. Sorry if I'm butchering the last name. And he'll be talking about accretion ejection theory when has the magnetic field become indisputable. Take it away.
Thank you very much, and good morning, everybody. So thank you for the organizers to giving the opportunity to give this short talk. So I will first make a short historical perspective or presentation of the various accretion ejection models before going to the jet emitting disc model and describing some of the main properties of this model. And then go back to the field of young stellar objects, because I think in the last years, very important things came up, and that will be of relevancy of what we have done and discussing in this conference. And because it seems now that it is more or less clear that we really need to have large-scale magnetic fields in accretion disks, even in young stars. So then I will discuss some consequences of the presence of such a large-scale field in disks. So we start with jets, of course, because we know they are present in almost all classes of accreting objects. And can you see my pointer here?
Yeah, we can. Yes.
Yeah, okay, thank you. So we know that their morphology can be quite the same, regardless of the accreting object, be it like a black hole or a young star. And if you look at the power, there are many ways to look at correlations between what is coming from the jet and what is coming from the accretion disk. But more or less, there has been this tentative to put all accreting objects in the same plot. Of course, we can argue a lot about this, but basically what you can see is that regardless of the central object, you have more or less about 10% of the power that goes into the jets in terms of kinetic power with respect to what is provided in your accretion disk. So if we were to use Occam's razor blade law of parsimony, then you would look for a universal model or process. And the other thing which is universal in all these objects is, of course, the fact that there is an accretion disk which is around it. So it is natural to look for an accretion-related process allowing to provide the jets. But if you go to the history, of course, what was important initially was to explain accretion and only accretion, which is a way to convert the mechanical energy of a rotating material around a central object and provide the correct spectra. And so the first model for this was, of course, the seminal Chakwas-Sunyaev model, which is now called the standard accretion disk. So there are various acronyms here, which is a geometrically thin, highly subsonic accretion, which takes place because there is some kind of turbulent viscosity. And in the paper, there is a mention of the magnetic field, which is here, which is the only thing which was needed was to have like a turbulent small scale magnetic field so that you get turbulence. And of course, we all know that it took a long time to find out a process, which is the magneto-rotational instability that came up in 91, but to explain at the end this alpha. But for this model, there is no need of magnetic fields. It's a pure hydrodynamical model. Later, it was recognized that actually we are not dealing with fluids, but we are dealing with plasmas. And in plasmas, you have electrons and ions. And in order to have a thermalized plasma, you need to have enough collisions. And to have enough collisions, you need to have enough density. So if the density is too small, there will be no more thermalization. And you may have a plasma, two-temperature plasma. And this is called, in that case, you have ions that become much hotter than electrons. And then you get what is called the ADAF or the RIAF or whatever you want to use, but something in which you have much less energy radiated. So that if you look at the energy budget of such accretion flows, what is available as energy goes either in radiation from the disk or being kept in your flow, which is eventually going into the central object. So if the disk is geometrically thin, then you have a standard accretion disk, and mostly everything is radiated. But as long as your disk gets puffed up and hot, then you may have everything being advected, and that's fine. And there have been a lot of studies explaining all the parameter space in accretion rate, going from like ADAF-like to slim, optically thick, accretion flows. There is no need to have a large-scale magnetic field for that, as long as you have a turbulence, which is everything encapsulated in the alpha parameter. But in those models, there is no explanation for jets. When it came for jets, the first explanation was actually the same for AGN by Blanford and Rees and young stellar objects by Canto, which was the idea that you had some source providing a supersonic spherically symmetric wind that will become eventually collimated thanks to outer pressure. This was some kind of de Laval nozzle acceleration. And it became soon very clear that it was impossible. And now images clearly show, either in AGN, for instance, or in young stars, that collimation needs to be at work very, very soon, close to the accretion disk, and that acceleration and collimation are processes that need to go along together. And the only possibility that we came up with is large-scale magnetic fields, really large-scale magnetic fields. So now the question is, what is the magnitude or the importance of the magnetic flux which is available? If you think that your central object has not much magnetic flux available, and that the magnetic field is strong in only close to the central object, here a black hole, then you end up with a jet that would mostly extract the rotational energy of space, or say of the black hole, which is then carrying space around it, and which is the Blanford-eject process. If, on the other hand, you think that there is a large magnetic flux available, then you eventually end up with magnetic field which is also threading the accretion disk, and that gives it's the idea of Blanford and Payne magnetocentrifugal acceleration. And the good thing with this model, Blanford and Payne, is it was structurable analytically. And Blanford and Payne showed indeed the possibility to explain collimation. And later it was generalized to relativistic flows by Lee et al., Vlahakis, and people like this. But the action of this flow here on the accretion disk itself was not computed in these models. So this was done by in the framework of the Jet Emitting Disc, which is a model in which the main assumption is that you have a central object, whatever it is, could be a star, could be a black hole. What is important is coming from the disk, and that you have a magnetic field threading your disk everywhere. So the magnitude of this magnetic field is measured by the magnetization here. And since you expect outflows, of course, the accretion rate cannot be constant with the radius in a steady state picture. It needs to decrease as you go inwards. So this is measured by this psi exponent here, which is the disk ejection efficiency. The smaller it is, the less mass is being ejected. And because the less mass is being ejected, it means also that the higher velocity you get. So the velocity is not related directly to the strength of magnetic field, not yet, but to how much mass is being ejected. And this kind of model solves the full set of MHD equations and is, in a way, an exact mathematical solution. So what are the main properties of this model? It has been shown that you need to have a near equipartition large-scale magnetic field. This was the price to pay to get a self-confined Blanford and Payne, and you have here different sets of those solutions. And you see the scales here in units of the anchoring radius. They can be quite fast, quite large. Second is that because the magnetic field is so strong, accretion is the dominant torque is due to the jet, and accretion is supersonic over the whole jet radial extent. Because it is supersonic, it means that sonic waves cannot propagate upstream, and so there is no way that there will be some kind of solid body precession, at least over the whole jet radial extent. And for a given m dot, since the velocity is quite fast, then of course the density is smaller. So for a given m dot, you will have very easily optically thin hot solutions, which can be very common. And this has been already computed and shown here. And if you look at the energy budget of such accretion ejection flows, so it means that the available energy can be shared now into radiation from the disk, advection, of course, but then power into the jets. So because there's a significant amount of the power that goes into the jet, it means also that the disks are much less luminous than their BZ-free counterparts. And also a remark here, as in those models, you can use h/r, the disk thickness, as a free parameter, which is here. And you see that as it becomes large, the jet power goes to zero, almost to zero. And this can be easily understood, is that a magnetocentrifugally driven wind or jet requires matter to be rotating. And if you have strong magnetic fields and a very puffed up disk, then at the surface of the disk, material is not rotating anymore. So there is no way to have a magnetic jet. You may have like a thermally driven winds, yes, but no powerful jets. So these are the properties of jets, analytical properties of jets. And now it comes after the 2000 years, there has been the advent of high performance computers. And this allowed to going from the sketch to real, I would say, systems where you could see how it evolves. And starting with like a initial condition, like this, for instance, this is the black hole. You have a big torus and you use magnetic fields initially. You need to have magnetic fields in order to trigger MRI. And then eventually you end up with these accreting flows here. And what has been observed is that the magnetic field is advected, actually, and you build up something which resembles pictures like this one. And at the same time, it has been nicely shown that the Blandford-Snezek process actually is at work, although the properties of the jet coming here are very much sensitive to numerical aspects like the density flow, for instance, and of course, how much magnetic flux has been provided initially. For instance, if you start with no BZ field here, then you don't get jets here. So there are some aspects which remained opened. And if you look at what has been discussed already and already in this conference, the first studies termed this inner region here called a MAD, for a magnetically arrested disk. So this MAD model came initially from the spherical accretion, and when magnetic field buildup will be so strong that it will eventually stop material to rotate, right? And indeed, as a function of time, you see that the magnetic flux is increasing until it reaches more or less a steady state picture. And I would say steady state more or less. And here you have the radial profiles. And below this red line here, you would have what is being called more or less a MAD system, in which you see in this curve here, you have equipartition between the magnetic energy and the thermal energy. But in fact, it turns out that this material here is not arrested at all, actually. It is still rotating. And so that's why McKinney et al. Proposed MCF, which had not much success because I guess the MAD, using a MAD name is nice, so much nicer than MCF. But anyway, it is not rotating. It is rotating, sorry. So through the advent of these fantastic observations, the names like MAD or SANE became very popular. And but I would like to stress that a MAD, and especially outside the ergosphere, it looks very strangely much like a jet. And also, to be sure of that, then we need to go and analyze, which is something that still needs to be done, the dynamics, which is what is the dominant torque, how is the sustained turbulence required in order for the material to go through the magnetic field lines? What is the magnetic diffusivity? And also what is the mass loss? So there are, of course, some studies, and I didn't cite all of them, but this remains to be done. When it comes to jets, then initially the focus was on the spine, which is the Blandford-Snezek jet. But now clearly the observations tell us that it is the sheath around. So the interaction with what is called the disk when. So there is an increasing role of the disk in this community. And then I switch and I go for YSOs. In YSOs, the problem is very different. In YSOs, we are not sure actually that the disk is fully ionized. In fact, it cannot be. The outer parts of a circumstellar accretion disk are not dense enough so that cosmic rays can ionize it. And then, of course, you can use, let's say, MHD here, usual ideal MHD. In the inner parts, it is enough warm so that collisional ionization works. And again, you can do ideal MHD. And if you do that, then you can compute like using 3D shearing box simulations, and you can compute like the alpha parameter. And this has been done for like 20 years or so. And now we know, for instance, that the alpha parameter scales with the magnetization with this way here. And to explain, for instance, accretion onto the star, well, people rely on magnetization as small as this one, 10 to the minus 4, 10 to the minus 5. But this is for ideal MHD. There will be a zone, and the first, yes?
You've got 5 minutes remaining.
Oh, okay. So where in this zone here, it cannot be ionized, and you need to take into account non-ideal MHD effects. If you take into account non-ideal MHD effects like the Hall effect or ambipolar diffusion, then it turns out that the disk cannot be turbulent. It needs to be laminar. And if it is laminar, then there is no way to have accretion. So how it can accretion which is observed. So the idea is that you need for another agent in the laminar zone, and this can be the winds. So the idea that winds are absolutely necessary to allow accretion came up in this community. And to get those winds that carry angular momentum from the disk, it means that you have to have a large scale magnetic field. So to assess this, you need to go to 3D large scale simulations. And this has been done recently. It's quite hard to do. And Zhu and Stone did it. And they obtain, you have here the outcome of the simulation. And it looks like the GRMHD simulations, if you wish. The magnetization is very, very small here. And then you have this super Bernfeld and Payne-kind jet, super fast and super galvanic. And there's a tension with the old jet calculations. So we came back to this problem. And with a PhD student, we computed new solutions, allowing this time MRI to be active in the disk, and allowing here, the wavelength. We proved that MRI could indeed allow to help jets to occur. And so this is the parameter space that we came up with. This is the magnetization, and here this is the ejection efficiency. As you can see, the old jet simulations with supersonic accretion speed are here, and you have other set of solutions here. So in a way, we were quite happy because we could recover analytically what was observed in simulations. The problem is that the simulations, the disk was puffed up. If you look here, this is the VZ and this is the radial speed. You see that the disk, the thin disk, is actually, its vertical structure is on 10 scale heights, not 1 or 2. It's 10 scale heights, and outflow comes only far away above it. While by assumption in the analytical model was assumed it was just H. So we did 3D global simulations. So basically the same as Zhu and Stone, and then we analyzed the outcome of the simulation. And we found out that the disk is indeed geometrically thin, turbulent, but there is a new zone here, turbulent, and winds comes just above. And this is MRI active here. And in this zone here there's a supersonic accretion, while here is highly subsonic. But the mass-weighted accretion overall, it remains subsonic, consistent with the magnetization. But the fact that you have a zone here which is highly supersonic, allows to advect magnetic field. So if you start with a small, low magnetization disk, you end up with a solution which is more or less sketched here, which is a quite puffed disk, where supersonic accretion accretes here and brings in magnetic flux towards the central object. If your magnetic field is much stronger, then you have a runaway process, and you end up with something which is, well, in a jet, actually, because you have a zone here, you see it here, where the magnetization is around unity, and you have a Blanford-Payne kind of jet. So the consequences of this large-scale magnetic field is that then you need to think in terms of two independent stuff, which is brought in by the object or by outer reservoir, mass and magnetic field. Of course, they are related.
1 minute, Jonathan.
Yes, thank you. They are related, but they are two actually independent quantities. And this has been shown that this is quite fruitful to explain some cycles in X-ray binaries. The thing is that there is no more such a thing as a standard accretion disk. If there is a large magnetic field in accretion disks, then you will end up with such a structure. And you will always have winds. And if you have winds, then they will carry angular momentum and will even affect your disk, right? Since you are bringing in magnetic field, it will eventually interact with the central object. So it means that in terms of jets, you have to think of jets as multi-components outflows. You will have, if it's a star, a stellar wind. You will have, if it's a black hole, a Blanford-Payne process. But of course, you will have some kind of interaction between the two. And the way they interact and the outer outcome of the collimation will depend on the available magnetic flux that you have in your disk, okay? So I will end up with these two philosophical comments, is that it seems now that for the last 10 years in both communities, that the existence of a large magnetic field is quite, let's say, accepted. It's some kind of our dark matter, right, in our community, because it is still undetected, but has a dramatic dynamical implications. But if there is no large magnetic fields, like in the objects, then since we need to explain jets, we have to rely on in dynamo, and there are many interesting works on this. The thing is, if you still need to rely on a universal picture, then you have to think of a dynamo that should work on every object. And oops, sorry. I will also make an advice is like high performance computations allow to have fantastic results. The problem is that they are very, very hard and very complex, but still we need to not only observe the results that we have, but try to understand them. And to understand them, we need to go back to analytical models and compare both. And this is a very fruitful collaboration when you put both analytics and computations together. Thank you very much.
Any questions in the room? We have one.
Thank you very much, Jonathan. I like very much your universal attitude towards explaining all of them. I think this is the secret. We have to think that always that the jets are seen in so many different things, from black hole, from white dwarfs to AGN. With the BZ, the magnetic field along the axis, in my opinion, it has to be produced locally, because when the sources cross the jet line and go to the left and the jet disappears, then cross the jet line to the right and the jet appears within an hour, the magnetic field cannot come from far away. The source ought to have anticipated that it will cross the jet line backwards, so as to order magnetic field from far away. Nature doesn't work like this. The magnetic field somehow must be produced locally.
Again, we need numbers here, because you have to think, it's always hard to realize this, but the Keplerian the dynamical time scale is around a millisecond, right? So there's plenty of time to do things in, say, 0.1 second or 1 second. And so we need to put numbers, because the time it takes for a jet to be launched and to be detected may give a lot of time to advect field not so far away. I'm not saying that you need to take your field from the outskirts of the accretion disk. It's just that you need to build up enough magnetization. And magnetization is not only the magnetic field, is the magnetic field divided by the pressure. So the mass, if you wish. So as long as the magnetization is strong enough, and you can play with the BZ or sigma, and both, because they will be related, of course, then you may have time to do what you want. But again, I agree with you, you need to put numbers.
I see a hand up in Zoom. Asaf, you can ask your question.
Thank you for an excellent talk. Two questions. One is kind of continuation of the question by Nick. What supports the large-scale BZ field in the case of ideal MHD? Now with the first question, and the second question, which is kind of related, we know that in these MHD simulations, the jets are virtually empty. There are no material in there. So where do you think what really happens in reality, to your opinion there?
Okay, in ideal MHD, so you mean in young stars, right? There is no constraint.
X-ray binaries, right? Essentially, you argue that you require large-scale magnetic field with essentially a long coherent length. So where is this field supported by? Because if the disk must be turbulentic in order to enable accretion, then how do you get this long, large coherence length essentially, which you asked?
Okay, it's again the chicken and the egg problem in a way. It's like, because in those ideal MHD simulations, or like the ones we have done here and analyzed, you start initially already with a large scale magnetic field, okay? So it is already there. I fully agree with you. What you see is that if it is already there, it gets unavoidably advected.
That I got no problem. But then
okay, so now, when you say I say that it is a large scale magnetic field, I say that it is current length is larger than, say, h, right, or 10h. Now, if the magnetic field indeed has been advected, so you ask this question quite far away, right? Then the h that you have at the outskirts of the disk, if you imagine like loops, right, in the outskirts of the accretion disk of size of h, will be quite far. If they get advected, then you may have amplification. You will, of course, open them. And you may have what I think Matthew Liska showed in his simulations, in 2020 simulations, right? Is that you may have eventually the buildup of a zone with a given polarity. But I agree. I mean, the fact that something which was, let's say, termed small scale in the outer parts may be advected and becomes large scale in the inner parts is a global process. Or, as Nick said, well, you may rely on dynamo, right? But I've seen never, ever any dynamo being able to build up a large-scale field from a small-scale field. And I'm not saying it exists. I'm just saying I never saw it, never.
Okay, so it's an open question essentially.
It is an open question, yes.
I'm sorry, I'll have to cut you off here because I would like to take another question. Sarah, please go ahead with your question.
Oh, hi. Actually, I think this is kind of carrying on from the last discussion. So maybe, we can also move it to chat. But let me just say quickly, I mean, you mentioned Matthew's simulation, and what they showed was actually the fact that most of the prior simulations, were so low resolution, they couldn't actually build up the field. And when you get to high resolution, you do exactly get the dynamo. But I wanted to ask, maybe you've seen the work by Sean Ressler. They've actually done for Sagittarius A star, starting with the magnetic fields in the stars, doing a global simulation, and showed that bringing it in down to the black hole seems to work in terms of giving you enough magnetic fields to be generated to actually explain the observations. And I wondered if this could be scaled, in your opinion, to X-ray binaries, so, looking at these results more directed towards AGN, do you think that the X-ray binary companions can give us enough seed fields to reproduce this kind of result?
Well, we all have this picture in mind, right? I guess. It's something in the binaries is more or less this. So we are, material which is coming here is ionized plasma. So it's carrying magnetic field. It's carrying magnetic field with the scale of the plasma. So that's what I was saying here is that here, I can't imagine why there will be no magnetic flux coming in, brought in here, right? The question now is something which is still open because I'm not sure we understood in Matthew's work, for instance, but he's here. So, I hope we will be able to have a discussion on this. How come that a small scale field here, let's say B phi, okay, and then you have, of course, you will have, because you have indeed MRI dynamo, but when people say MRI dynamo, it says, you know, this butterfly diagram on small scale fields, always small scale. And this is on smaller or maximum H scale here, but the H scale here is tremendously large with respect to the H scale here. And now the question is, how come you build up one polarity zone here? And this is, well, this is not clear to me how it happens. Maybe we observe it in the simulations and okay, that's fine, but I'm not sure we understand it, how it happens. But basically, indeed, what we have done is that in this region here where we know ideal MHD applies, well, it seems quite unavoidable or normal that we have already a large-scale field here built from this all the way down here. But the way it is built up, this I don't know.
Okay, well, let's move this to the discussion.
Yeah.
I think when Matthew's awake.
Yes.
All right, let's thank Jonathan again.
Thank you.